The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our second tribute presentation of this symposium is by Andrea Shocker, and that would be on the contributions of Morris Schupack to the field of corrosion of metals in concrete. Andrea, I think in the program book, is listed as professor and head of civil engineering at University of Minnesota Duluth. But if I understand correctly, now she is executive vice chancellor at that school. Congratulations on the promotion, which was recently. With that, Andrea?
Yes, as the faculty like to say, I recently joined the dark side of administration, so I'm not participating in as much teaching and research these days, but I'm very, very honored to be here at the symposium to talk about the contributions of Morris Schupack. As a graduate student studying corrosion and post-tensioning, both Hope and Schupack were people I'd read many, many articles from. And when I came and sat in on some of the first 222 meetings in corrosion, it was exciting to see the real Brian Hope and the real Morris Schupack in person at those meetings and see all the contributions that they've given us over the years. This is Morris, and he's unfortunately not able to join us today. Maury, whether you know it or not, is well into his 90s, and I talked to him the other day on the phone, and he sounds great, but he said his body is not cooperating the way he'd like, and so he wasn't able to join us. He came for many, many, many years to ACI regularly and has been a huge contributor to all these committees that are listed here. I've sat with him on both the Pre-Stressed Concrete Committee and the Corrosion and Metals and Concrete Committee. If you've been on committees with him, you know that he always had many, many responses to the ballots, had long lists of things if you were in charge to have to go through and respond. And while that sometimes is frustrating, I always found that the things that he put in his ballot were very important things for us to consider, and that time was well spent. He still does that, I believe, is still very active in responding to ballots, even though he isn't able to come as much anymore. He also was on the tanks committees, development and splicing of deformed bars, and the FRP committee, ACI 440. Tanks was a big passion of his. I know that when we were working on documents, particularly the pre-stress committee, if we didn't write down tanks, then we were in trouble and we had to go back and look at it again. So I appreciate that background as well. Maury would only give me pictures of grout, and tanks and things. So I don't have any wonderful young pictures of Maury or family pictures of Maury, because when I asked for pictures, I kept getting more grout pictures. So I finally gave up. Maury was also the 1990 recipient of the ACI Arthur Boys Award for his pioneering work on the development of pre-stressed concrete and tireless efforts to improve durability of structural concrete through innovative development in materials technology and unselfish service with technical committees. I would guess we're well into the thousands of hours that he's put into ACI with his contributions on the committees. Maury is not an academic. He is a consulting structural engineer and had a very interesting background. At the age of 15, living in Brooklyn, he took a course in structural engineering at the Polytech, and he still says today that this was the best educational experience he ever had, was this course at 15. That combined all the theory and mechanics and structural design along with hands-on time in their steel fabrication lab. And then to test out his ingenuity, he went around the neighborhood and repaired all of the steel cellar doors for his neighbors using leftover bed frames and things like that, and then taking them to the fabrication lab to finish up. So a very ingenious engineer from the very beginning. In 1939, he started college at Brooklyn Polytech and then moved to George Washington University in 1940. At that time, he was also working as a civilian draftsman for the Corps of Engineers. And in 1941, as a GI, he was selected for a year of civil engineering specialist training at The Ohio State University. After that year, he was sent to France as a construction specialist, and those quotes are his. He said, "I'm not sure what a construction specialist is, but they told me I was going to France with a 50-man detachment and would be constructing 3,000-bed hospital laundries." This one he also said tongue-in-cheek that he was made staff sergeant. One day they called him in and said, "Due to your superior technical savvy, we are promoting you to staff sergeant." He says he wasn't sure what that superior technical savvy was, but he was happy to be promoted. He then, in 1947, after the war, returned to Ohio. Well, actually, after the war, he returned to Ohio University under the GI Bill and received his degree in civil engineering, his full degree, in 1947. So he'd already had a lot of practice as an engineer at this point by the time he received his degree in 47. From there, he went to design steel bridges for Steinman, Ammann, and Whitney. And by 1951, he joined Preload Company, eventually becoming their chief engineer and VP. And this was a pioneer in the post-tensioning pre-stressing fields. And in fact, Morris sent me one time, he keeps all of his documents, and he said, "Would you like to see the patents from post-tensioning, the early days?" And I said, "That would be great. I'll write a little paper about the history," which I did for another symposium. And he sent me 2 huge boxes full of all the files of every patent that they were looking at in those days. And it was completely fascinating. It was like sitting in the library stacks going through some of the craziest things I've ever seen for potential post-tension anchorages, but also at the development of what we have today. And then the correspondence between the couple companies that were working in this area from the day. So it was a neat historical record, and he was really part of this whole development, particularly in the post-tension industry. He started his own consulting practice in the late 50s and specialized in pre-stressed concrete structures, and since then, that's basically been his focus for different types of companies. He's investigated over 200 pre-stressed steel corrosion incidents is what he calls them, but typically problems, about half of which were the pre-stressed tanks, and about the other half was unbonded post-tensioning problems, with the other 10% being other things. He's a past board member not only of the American Concrete Institute, but also of the Precast Pre-Stressed Concrete Institute and the Post-Tension Institute. ACI first, the PCI and PTI developed from there. So he's been active in all those. I know him very well also from the PTI committees. He's extremely active on the Grouting committee there, and with tanks, of course. He's got over 70 articles and numerous reports. I found when I started to talk to him, I met him as a graduate student, and I'll have a story about that towards the end. But once I met Maury, he's got an article for anything you can imagine. If I needed something on some aspect of grout, he's got it in his files. It may have been published in something that I haven't heard of, but he's got it, and he's got all the details, and had already investigated a lot of the things that I thought were new. So one of his areas is pre-stressed tanks, and this is another case where he was involved nearly from the beginning. So some of the early pre-stressing in the United States was the pre-stressed tanks. And his focus was on improving the designs, particularly with the very, very large tanks, and also looking at the corrosion protection, knowing the importance of that in this type of structure. He's investigated over 100 tanks and published very widely in this subject. He has quite a few patents, both in grouting and also there's some in tanks. If you look up his name in the patent office, there's quite a few in there. One of the ones he talks about is in the electrically isolated tendons for corrosion monitoring and protection from stray current. So this is a way to electrically isolate the whole anchorage and strand system. And this is his 1982 patent. And in that patent, if you look it up, there are many, many different configurations of this, most of which look very much like what you'd see today in an electrically isolated tendon. Post-tensioning grout. This is the part I know most about Maury, as one of the other couple people who work in the post-tensioning grout area. He recognized the bleed problem that we still wrestle with in post-tensioning grout back in the early 60s. He was working with a lot of the taller nuclear structures at the time and started seeing the water collect and started studying what was actually going on there. So I don't have my grout primer here, but essentially what you get in a post-tensioning tendon is a pressure head develops in the grout, and that squeezes water to the top. And if you have strand particularly, it filters the water and helps you collect a large bleed lens, which then can reabsorb or evaporate or stay there, but leaves that piece of strand or bar tendon vulnerable to corrosion and other problems. So the higher the pressure head and the more strand, the more you see this. And if you look at these types of structures that he was looking at, 150 feet, 180 feet, these are huge, huge vertical rises that cause a lot of pressure and very large strand tendons in many cases. So he started doing these mock-ups in the 60s at full height. They would attach them to the outside of the tank with some clear duct and take a look at what happens, and found that there were feet and feet of water that were developing at different points along these tendons. So he decided to do something about that. Some of his early tests were a 150-foot tall one with vertical bar tendons. Now, the bars didn't wick, but they still caused a lot of pressure head. Then when he started a strand tendon, he did 180 feet with a 54-strand, half-inch diameter strand tendon. It's a lot of strand, a lot of filtering, and some of my students are here today. You've seen in the lab the kind of water we get with a small little duct and, 12-strand. This is a whole different ballgame. So what he decided to do is take care of that problem by developing a new admixture, a new grouting material. Again, this was in the late 60s and early 70s. And he developed a pressure bleed test, and this is a picture of it here. And I'll show on the next page how this all works. And for a long time, this was called the Gelman pressure test. And I looked up Gelman at one point when I was trying to find the filter. And Gelman is the manufacturer of the cylinder, which is used for food testing, for separation of food testing. So eventually we decided to name this test in honor of Maury, and so it became the Schupack test in the PTI specifications. It has since become recently an ASTM specification for pressure testing, filter pressure testing. It's a very interesting way of handling both the filtering and the pressure test, and my personal belief is to this day this is the best bench scale test we have for looking at this. Okay, we have some other types of mock-ups and things to try to get the real scenario, but it's not easy to build those large mock-ups, especially if you're looking at a case of 180 feet with a 54-strand tendon. So I still think that this is a really effective test for trying to get a feel for if a grout has that type of bleed resistance. He found this, he did this test in conjunction with trying to develop a grout that would withstand this type of pressure and filtering. And so during that time, he developed the first thixotropic or water-retentive grout admixture that stopped the bleeding in grouts. And this early admixture was very effective. And this would hard to do with grouts today. It was a much thicker grout than what we see today, much more gel-like, but they still were able to pump it in hot conditions. And this grout could successfully pass that 180-foot high test with no bleed visible in a clear duct. That's not a small feat. This is what the test is. You fill up this little small 200 milliliter stainless steel funnel with grout, and you have a pressurized air, and you push the water out of the grout. In the bottom is a small stainless steel screen and then a fiberglass filter that's supposed to mimic the filtering effects of the strands. Now, it's not the perfect scenario, but it's pretty darn good compared to a 180-foot tall tendon versus a very small benchtop setup, and is effectively used particularly to screen out the low-end grouts that are not going to be applicable for kind of 10-foot rises and below. I pulled this from a paper. He did a historical review recently. Well, not recently. In 2004, he had a paper in Concrete International, and he had sent this to me saying, oh, there's good pictures in here, but I kind of liked that he had his list of grouting myths. So these are Maury's grouting myths, and I thought, that'd be interesting to see what he's got here. Pressure and lock-off as a final grouting step. Pressure and lock-off as a final step to eliminate voids. In other words, he doesn't think you need to do that. I happen to agree. It turned out that I agree with him on every one of these, I think, so I was excited about that. Grout has to be visibly flowable to fill the duct. Grouts can't be pumped above 80 degrees Fahrenheit without ice. Energy mixers alone, high-energy mixers will control bleed. The little beaker bleed test is informative. So, in other words, none of these are true, in his opinion. Thixotropic grouts need a very high pressure to pump. Expansive grout is beneficial if you lock under pressure. Topping off vertical tendons after bleed occurs provides adequate corrosion protection. The ASTM flow cone test, which we still use by spec, is a meaningful test for pumpability. Grout strength is more important than filling ducts and spaces between pre-stressing steels. So he believes all these are myths, and I agree with all of them from 2004. We still fight a lot of this stuff today, and I think that his knowledge in this area over the past, 50-some years was right on the money. I really think that he thought of things way ahead of time. His suggested research areas from 2004, if I just knew that he could just hand these over to me, that would have been nice, but I figured out some of these out myself along the way. But this is basically having to do with a lot of the things we still fight with. Vacuum grouting, venting, the practices of locking off and pressurizing tendons, how do we get rid of voids in very complex spaces, all these types of things, also from that same paper. And I'll tell you, as a graduate student, what I found when I went to my first conference that I'll talk about at ACI and presented my grout research, I thought that no one had done that stuff, because it just wasn't a very exciting field, grout. Who does research on grout? Little did I know. But what I found out is over half the things that I did had been done 30, 40 years earlier by Maury. So we became very good friends to talk about the different things that were going on in grout. And he was glad to see a revival of someone finally listening. I felt that from him for a long time because he went through a lot of this in 1960s and the 70s. And the bridge industry, for instance, in the United States did not pay attention to this problem until the late 90s. So the fact that we were able to connect and use the experience that he'd done so many years ago, I think was vindicating for him and also very helpful for me because he shared freely with what he'd done before and worked with me. Here's one of his, I pulled some figures from his test. This is 1970, 138-foot high tendon. The students in here who have done some of these in the lab can be very impressed with the scheme of this. So they did full-on mock-ups of these things. Here's a 170-foot high one with the 54 half-inch diameter strands, Schedule 80 pipe. It says that they saw no bleed water voids from the exterior of this, and they chopped a lot of these up. I have slice pictures of that as well. And the specs now that talk about the Schupack test and some of the bleed parameters came from comparisons to these actual tests, which we have never repeated this height of test because of just the feasibility of doing it. My lab can't handle that sort of thing. Here's a really nice parabolic tendon drape. You can see the size in the pictures there. They did some work with very large tendon curved beams. Basically, he's looking very specifically at the tank type situation here. Here's some of the voids. 1967, they're seeing all these voids between the wire and the strand. And then I like this picture because this is another what I think is a myth, is that you can't get this thixotropic grout between the wires and between the strands when they're tensioned. And this is an absolutely perfect slice of tendon with completely filled grout from that same 54-strand test that they did back in 1969. And so I'll finish up by talking about how I met Morris Schupack. It was at the Spring ACI Convention in 1998. I was still a graduate student at that time, and it was in Houston. I knew it was in Texas. I had to look up if it was in Houston or Dallas. And I'd gone to do some other conventions, but I hadn't been to ACI before, and my professor, Jack Breen, paid for me to go. So I came along, and I had my paper on my research in progress about high-performance grouts, which I was pretty sure no one would care about. And that was probably fairly true, except for there was a very important person in the audience that day. This is me around that time. playing with grout out in Texas at UT. And I stood up and gave my talk and talked about the Gelman pressure test and, naively had no idea that sitting in the audience was Schupack. And I went on. And that day was important because someone stood up in the audience and said, "So, how did you think that Gelman test worked? Do you think that thing's any good?" And I said, "Well, yeah, actually, I think it's a really good test." Most important words in my career, because he said, "Well," he said, "Well, I'm Morris Schupack, and I developed that test." And then he sat down, and I kind of, and I left that talk and talked to him later that day outside for hours. And he talked about the excitement of having someone working in the field again and getting on some of the committees and helped me personally out a lot. And I think he's helped our industry out a great deal. And I'm really proud to have known him and to have been sit on 222 with Maury and Brian. So I'll finish up. Thank you. Thanks.